What are the causes of climate change? The easy answer is alterations that change the energy balance of the Earth. Things that change absorption, things that change reflection, alternatively changes to the forcing. The question is, what are the things that can actually do this? So the causes. The causes break down into natural causes versus causes that are associated with humans, anthropogenic causes. First, I'm going to go through the three natural causes that cause climate variability or potentially climate change if it were to persist. And then I'm going to essentially the three man-made ones. So again, it gets down to something that's sort of countably manageable. One of the natural mechanisms are changes in the sun. And this is one of those neat pictures that NASA makes that shows 11-year sunspot cycles with the bright white things on there being sunspots. You go through these maxima and these minima of sunspots, and if you measure the amount of energy that comes off the sun, that is associated with about a 1% change in solar energy. And so it becomes the scientist's job to understand what does 1% variability in incoming solar energy do to the climate. The answer is not a lot, but it's very measurable, and it's a very active field of study. And if you're way up at the edge of the atmosphere, it does a whole lot more. So the atmosphere, this is the ionosphere protecting us from, say, solar storms for the most part. The next natural mechanism, and the one that gets a lot of attention, are volcanoes, and in particular with volcanoes, the role of dust, which is a very intuitive feel, and more generally something called aerosols, where aerosols are really any particulate matter that's suspended in the atmosphere. So dust is a subset of aerosols. But most of the aerosols we think about are liquid in some way. You know, a little raindrop is also perhaps an aerosol, but we consider them in a different class. So when we think of aerosols, we think things like sulfate droplets, little droplets that have perhaps potentially a lot of sulfuric acid in it. We think about ash. We have a whole category of fine particles of ammonium chloride or something like that, which will then, water will cling to them and they'll become aerosols. So they're natural aerosols, and volcanoes are responsible for these sort of big impulses, really, of aerosols that can be alive and be active in the atmosphere 5-6 years at a time if it's a very large explosion. Volcanoes are what get people to thinking about geoengineering because they have a discernible cooling effect on the planet. And then the next cause of climate variability, or natural cause of climate change, is the one that, in my field, it's often called internal variability, a term that I also have come to realize doesn't convey very well at times what internal variability is. You could think of it as weather. Weather is part of internal variability, particularly if it's persistent weather. In Michigan, if you've been here long enough to see one of what we used to call a cold air outbreak, but now we call them polar vortex intrusions, where there's a cold Arctic air mass that comes and sits here for a week. That would be internal variability, this sort of persistent weather. And then there are a set of things that are mostly represented by exchange between the ocean and the atmosphere of heat. And what this picture is showing you is a couple of El Niños, where you're looking here at this case, sea surface height anomalies, but that's a proxy for temperature. And you'll see this is going to come over and it's going to get really big and white over in the eastern part of the Pacific. It's going to get purple over there in the western part, and it keeps bouncing back and forth. But what this really is some of that heat that went into the ocean is now coming back to the atmosphere. You're seeing exchanges of heat between the atmosphere and the ocean, and El Niño is one of the big causes of internal variability. And from a climate scientist perspective, this is either a great opportunity to study a process, or it's the noise that you have to deal with to extract your climate change signal out of it. So those are the three natural causes of climate variability and potentially climate change. Say if the sun were to persist in some sort of diminished solar output, you would get change responding to that. So the primary human source is this increase of carbon dioxide, and this is a figure that many of you may have seen before. It starts in 1958. I actually made this plot the night before last, so this includes the December of 2019 data in it. When this started in 1958, when these particular class of measurements started, we were already at 310 parts per million. When we started these, we were already above that, about 280, so already 30 above from industrial releases in the previous century. And you can see it goes up, has this annual cycle. This annual cycle is due to the breathing of the plants, primarily in the northern hemisphere. So what you're seeing is when spring starts, pull some carbon dioxide out. When fall comes, carbon dioxide is released back out. So there's this annual cycle, and you see this relentless increase. That is your primary forcing. Most of that, the biggest portion of that, comes from the emission of coal due to burning of coal, the emissions due to burning of coal. Another very large portion comes from deforestation and conversion of land. Then there's oil, there's natural gas, and then there's some percentage that's due to concrete cement making, which is sort of the other countable part of it. And then every year, a pretty big percentage of this carbon dioxide is either absorbed into the land or absorbed also in the ocean, because the ocean's also absorbing carbon dioxide, and that sort of mitigates this. I like to say there's one thing hopeful in this curve, which is if we had not done everything that we've done with renewable energy, which in a place like the United States and Europe has actually accounted for a large portion of the increase in energy use, this curve would be much worse. It conveys to people that in many cases we really haven't done anything about this, even though we've been talking about it for very seriously since the late 80s in terms of actually doing something about it. So that is your primary forcing. The data and some really nice graphics are at this link. A really cool animation of carbon dioxide for the last 800,000 years going through the ice ages is over there. The primary increase is coming from fossil fuel burning. Coal, oil, natural gas altogether greatly overwhelmed the deforestation. So the question is, why doesn't this thickening that I've used this metaphor of the atmosphere caused by carbon dioxide, why isn't there sort of a balancing in the reflection? The answer to that question is that carbon dioxide is active in the infrared, but it's not that active in the visual. So it's very much like a car in the summer where through the glass, heat up the seats, but a lot of that heat is kept in because that glass is visible to that heat energy that's inside, so the car just keeps cooking and cooking. The blanket is only selectively warming. You know, it's like having a special infrared blanket.
I'm curious on the kind of 800,000 year timeline, multiple ice ages, things like that, about how long it tends to take these cycles to come into balance in terms of like, you know, I've seen the graph that the amount of CO2 in the atmosphere now is much higher than it's ever been, but it's also been hotter than it currently is. So it's like, do we have some kind of what the time gap is between us pumping all this into the air versus then how long it would take the atmosphere to come into balance and settle at whatever new higher temperature we're going to be at?
So in the past, the Earth has been warmer and it's had more carbon dioxide in the very distant past, you know, millions of years. If you look at the ice age cycles, you will see that there's some variability in there. There's the time at the onset, at the time at the end, where you will see temperature or carbon dioxide. Either one can lead or either one can follow. Now, the reason you have that leading and following is that so much of the carbon dioxide is actually in the ocean. If the ocean gets warm for some reason, it can start emitting carbon dioxide. Carbon dioxide is in flux and in transport all over the planet in the same way heat energy is. The numbers of how long would it take to come into equilibrium, say if we just stopped our emissions today and maintained, that's probably on the order of decades, less than a century, that you would see some sort of equilibration. You still have the potential, of carbon dioxide coming out of the ocean in ways that, because there's some very carbon-rich water down deep if it were to suddenly come up. So aside from carbon dioxide, I want to mention there's methane, nitrous oxide, chlorofluorocarbons, and other industrial gases. And if you're thinking about policy and regulation, that becomes sort of a menu of things where you can trade one for the other in terms of heating potential. But carbon dioxide remains at this point the dominant one that we are concerned about. Well, the other human factors, the easy one is aerosols, smoke coming from fires. That's fires burning on the ground up there, smoke out of a smokestack. Air pollution. Aerosols are pretty complicated. They can heat, they can cool, which gets people who are into geoengineering exciting because that means they're a knob. And then the other big factor that humans are responsible for, land use change, and that changes both the reflection from the land, called the albedo, and the absorption by the land. And so this is the end of the things that we do. Land use, there are aerosols, and then there's the addition of the greenhouse gases are the human causes. And then on the natural causes, there was the sun, this internal variability, and again, aerosols. So what is interesting, if you're interested in studying it as a science, or what is perhaps frightening if you are concerned about how fast the planet will warm, are the feedbacks. Once we do that forcing, how does the planet, how does the atmosphere, how do the oceans respond? There are lots and lots of feedbacks. I'm just going to mention two, I believe, and one of them is the water vapor feedback. Remember, water is a greenhouse gas. Water is actually responsible for more than 2/3 of the greenhouse heating. Carbon dioxide is responsible for less than 1/3. When the planet heats, water evaporates, there's more water in the atmosphere, so you are increasing the greenhouse gas. So that is a positive feedback. The other feedback that's sort of intuitive and plays a big role in what's going on is what's known as the ice reflection or the ice albedo feedback, which is essentially that ice is white. White things reflect. So if you melt all the ice, then you're probably going to replace it with something dark that absorbs. And this is one of the things that's happening in the Arctic with Arctic sea ice. So sea ice is the ocean being ice, so it doesn't really contribute to sea level rise. The sea ice, if it melts and is replaced by dark ocean, that is another positive feedback. If soot gets on the ice, if those aerosols and turns it black, if farm dust gets on the ice, it causes it to melt more quickly. And we know that both the water vapor feedback and the ice albedo feedback are very active right now. So there are a bunch of feedbacks. There's the ice albedo and water feedback are positive and they're definitive. The feedbacks associated with melting in the Arctic are largely positive, and when I say that, as it melts, there is water vapor, there is carbon dioxide, there is methane in those frozen soils, in those frozen rocks. As they melt, you're releasing carbon dioxide that way, so that's another positive feedback. The feedback associated with clouds, because the clouds are white on top and dark from below, they can go both ways. And that is the most uncertain and a very controversial, and if you look at what's going to come out in the next IPCC report, it's going to throw a wrench into our ability to communicate this problem, because it's going to show much stronger sensitivities to the clouds and the aerosol feedbacks than previous models have. Aerosols are a bit the same. They're really complicated. They're made more complicated because they affect the clouds. But the theoretical and observational investigation at this point concludes that the Earth is a positive feedback system. I just want to emphasize this again, because I think in the next 1 to 5 years, if you stay up with what will be the political discourse, is I think the issues that are associated with clouds, and they're both positive and negative feedback roles, will lead to a lot of political as well as scientific discussion, if not controversy. So this is my last plot. This is a typical IPCC plot that is alarmingly complex. I'm going to attempt to say what is in this plot. Forcing is the change that's being caused by something. Right in the middle of that plot is zero, so that would be zero forcing. Things that are sitting to the right are a positive forcing. Things that are sitting to the left are negative forcing. Up and down the plot are different forcing agents. The top ones are gases: carbon dioxide, methane, the CFC or the halocarbons, nitrous oxide, N2O. That middle block I didn't really talk about. They are more reactive gases. They're sort of short-lived, so we don't worry about them as much. Then the one down there at the bottom that's got a lot of different colors and crosses the zero line, that's a lot of different types of aerosols. And then there's some cloud adjustments due to the aerosols. They're your most negative ones. So there's your hope in terms of self-regulation, in terms of the feedback of some sort of self-healing effect. Then there's albedo change due to land use, which right now is a little bit negative. There's changes in solar irradiance, which is very close to zero. We're in a very interesting time with the sun right now. And then over here on the right are our levels of confidence, with the VH being very high, the L being low. You can see what I said about the cloud adjustments due to aerosols are our lowest. But if you look down here at the bottom, there's your summary. Compared to 1750, so we've picked some in pre-industrial time, put in our best measurements through proxies of what the atmosphere were, and then we've changed the forcing, we've changed that radiative balance. So in 1950, that was about 0.5 watt per meter squared. In 1980, that was about 1.5 watts per meter squared. And in 2011, when this graph was made, it was a little over 2 watts per. And there's a history of this plot, which is produced in different versions with people struggling on communication strategies year after year. You can see a history of that at realclimate.org. And that is, in summary, what the forcings are and what's causing the climate change. You can see up there at the top the important role of carbon dioxide, and then next on that list, the role of methane.